All right, hello everybody. I'd like to welcome you to the Audio Programmer Meetup April edition. Thanks for joining the meetup, and we're glad to have you here. And we got some awesome guests with us today. Today, we're going to take a journey into the world of game, audio, and interactive media. And I'm here with Josh Rice and David Martilla from Nemesindo. So, before we get started, just wanted to make a couple announcements. If you're interested in audio software development and you want to learn how, be sure to join our community on Discord. That's at theaudioprogrammer.com/community. We also have recruitment, contracting, and bespoke audio software development services. You can check that out on our website, theaudioprogrammer.com. Second, I'd like to thank our sponsors. So they've been a big supporter of the Audio Programmer Meetup, and without them, this would not be possible. So thank you to our sponsors, Focusrite and JetBrains, and our two newest sponsors, Juice and the Audio Developer Conference. So they have now rejoined us as sponsors for the Audio Programmer Meetup, and we're really proud to be collaborating with them again. And with that, I'm going to make a couple announcements. So we have a few really awesome audio software development events that are happening. So if you happen to be in Tokyo, Japan on 17th of April, be sure to check out the Juice Meetup in Japan. For more information about that, check out forum.juice.com. And for the Audio Developer Conference, be sure to come out to Bristol for the Audio Developer Conference. That's on the 10th and running into the 12th. For more information on that, be sure to check out audio.dev. And another event that I just found out about that Josh is involved with is the 2025 AES International Conference on Artificial Intelligence and Machine Learning for Audio at Queen Mary University of London. Now that's a mouthful. So that's the first conference of its kind, and it's going to be at Queen Mary, and it's going to be a awesome event. You know that AI and machine learning is the rage right now for audio, and there are loads of questions and challenges and problems to solve around that, and that's what they're going to be discussing there. That's going to be happening on September 8th and running through the 10th. For more information on that, be sure to check out aes.org. And with that being said, we're going to pass on the mic to our presenters, Joshua Rice and David Martella from Nemesindo. And actually, before that, I just wanted to let you know for those information for those events, be sure to check the links for all those in the video description below. And with that, we'll go ahead and pass on the mic to Joshua Rice and David Martella from Nemesindo. And the name of this talk is going to be the next generation of procedural audio, and this is the abstract. We will talk about procedural audio or digital Foley. What is procedural audio? Rough overview of definition and history, followed by procedural audio in games. Why and how it is an area of opportunity. Then introducing how Nemesindo works, and we can show some demos while showcasing the future of procedural audio. And from that, I will pass it on to Joshua and David. Go ahead and take it away.
Okay, thanks, Josh, and hello, everyone. Hopefully, you can all see my screen with the title slide.
Yes,
Great.
all good.
So I'm going to just dive right in. Josh read the abstract, so you know a little bit about what it's about, but we'll define this whole area of procedural audio and specifically procedural sound effects. Um, and what are the big challenges? Namely, the lack of tooling for sound designers. So those, and I know many of the audio programmers audience are familiar with Juice. So it's allows you to sort of write code once and port it for many different plugin formats. Wouldn't it be great if there's a tool out there that allows you to port procedural audio for many formats as well? And we'll be talking about the sound quality issues. So when procedural audio is a generative sound, so there's always a question of does it sound like the real thing? and how we're going to address those. So this whole idea of write once, deploy everywhere, and merging the sort of traditional DSP approach to sound synthesis with modern neural network approaches, trying to get the best of both worlds. So that's what this talk will be about. I'll give a little brief introduction for Neversindo. So first off, it's the Zulu word for sound effects. Those who've been involved in company startups realize how challenging it is sometimes to find a name where the domain name hasn't been taken and where it's not too close to something else. So we settled on Namasindo, asked a colleague in South Africa to check that we did actually have the definition right there. But it spun out from research at Queen Mary, University of London, where I am right now in my office. And the whole point of the company is to translate all of the research we've been doing onto procedural audio into tools and technologies that can hopefully change sound design. So tools for sound designers and game developers, as well as partnerships with business customers and collaborators, mainly game studios. We're not the only one. There's a lot of, or a small number of great companies doing interesting things in this general area related to procedural sound effects. Kronos is a well-known one where they're not so much generating the sound, but they're coming up with wonderful ways to control in real time the sound recordings in very creative, innovative ways and for use in sound effects. 11 Labs is a fast-growing company who one of their tools, they're mainly known for vocal synthesis, but they do offer technologies for creating sound effects as well. And Tsugi offer the game synth platform for generating procedural models as well as other things. So that's just giving you a sense of what's happening. It is actually a fast-moving field. Um, and who are we? So, I'm one of the co-founders of Nemesindo, also currently CEO, past president a couple of years ago for my sins of the Audio Engineering Society. So got to see kind of a real big picture view of what's going on in audio there. And I've also been involved in several other startup companies. Lander, that was formed initially from research within my research team, as well as a company WaveShaper offering neural network solutions for real-time audio processing problems, and Roex, a quite new-ish company offering intelligent audio production. And with me is David Mortilla. Um, David, I will suggest that you do a little bit of introduction of yourself when it's your turn. I think that's much better than passing the microphone or me trying to speak for you. But David is the lead engineer working with me, and so he's the brains behind the technology at the moment and the one doing the hard work. So, what are we talking about? What are procedural sound effects? Um, First, procedural, there's a lot of definitions that have been given, and they're usually related to each other, but it's synthesized or generated on the fly. So real time, but not just real time. It needs to adapt to changing inputs. Um, so it could be a music generation system that is generating the music on the fly in real time. And if for some reason there's input saying it needs to be faster or louder or more dynamic or change in mood in a certain way, then those inputs allow the generative music to change according to those controls. But we're particularly focused on sound effects. So quite simply, we're looking at all the audio that is neither dialogue nor music. So explosion sounds, footstep sounds, environmental sounds, atmospheric sounds, science fiction sounds like phasers from Star Trek or lightsabers from Star Wars. All of those could be included in this field of procedural sound effects. And where did this originate from? So in the beginning, the first early video games, the only option was procedural sound because there was no space to store sound samples. There was certainly there wasn't the memory for them as well. So the sounds were primarily beat style sounds controlled by the actions in the game. So I'll play a little example here. I'm not going to play the whole 4.5 minutes of that, but you get the idea. Then people could do interesting, fun things going beyond the simple pop pop sounds from Pong. But these are all electronic computer sounds. They aren't meant to be in any sense realistic. And they do follow along with what's happening in the game, adapt maybe the speed and the choice of sounds that are being generated. But they are very limited in the types of sounds. So then there was quite a lot of research, and I think you can describe the emergence of the field with really three books. So it started with the work of Perry Cook, I think at Princeton, who wrote a book called Real Sound Synthesis for Interactive Applications, where he was essentially proposing what is now known as procedural audio, where he thought that the way to go with sound effects, things like footsteps, were to generate them in real time based on some physical model. And then Davide Recesso and Federico Fontana had a book based on their research called The Sounding Object, where it was more formal, generating more sounds based on a deeper understanding of the physics. And along came Andy Farnell, whose 2010 book Designing Sound really took a creative approach and said, can one, from just a programming point of view, by adding oscillators and modulators, create wonderful sounds that sound like realistic objects as well as environmental sounds and so on. So, based on that, the field really has grown into a very active research area with hundreds of papers proposing all sorts of models. Um, Now, procedural sound effects, they're still breaking into the field of game audio. So it is one approach that is growing in popularity and interest, but there's still challenges to it. And Foley is around. So Foley, named after Jack Foley, an early sound designer, is the art of creating sound effects by tapping your feet and putting a microphone next to it, or crinkling up paper and things. And these sorts of Foley type approaches have actually been used in video games as well. So here's some work from Paul Ware, the sound designer on No Man's Sky, showing how some of the animal sounds in that game were created.
Pause. So that's something that I can capture that as a rough performance. But all those values you see on there have randomization as well. They've got a little bit of jitter. So I can say, yeah, play that, but add or deduct elements of that. Also, we have this cool function, this will go wrong. But like Reaktor, we can randomize the presets. So just completely change it. So we start.
But even in games like No Man's Sky, where there are worlds created procedurally, there's still a lot of sounds that are pre-recorded sounds. And they have all the challenges of inflexible, uncreative sound taking up storage. So there's still a need for procedural audio to advance to the level of, say, computer-generated graphics in games, film, and more creative media. So there's a lot of techniques. It's not just one approach. FM synthesis is a popular approach for creating sort of science fiction type sounds. Some aeroacoustic sounds, impact sounds are very heavily informed by a deep understanding of the physics. Some involve waveguides, especially for things like vocalization or musical instrument type sounds, and so on. So it's not one approach, it's any approach that allows for real-time sound generation where the sounds can adapt and change based on live inputs. Um, The advantages, I mentioned them very briefly, but they include the low storage requirements, the flexibility and control, the ability to create infinite variations on sounds and sounds that have never before been recorded. Drawbacks, of course, there's CPU cost. That's not necessarily a drawback. It just means you choose those procedural approaches that are computationally efficient. But there's also a lack of tools out there and variable sound quality. Some models sound great, some need a lot of work. So at this point, I'm going to hand it over to David, who, among other things, is going to talk about how we address those two challenges. Thank you, everyone.
Yes, hi. Just briefly introduce myself. I'm David Martela. I'm currently a PhD researcher at the Center for Digital Music in the AI and Music program, working on specifically vocalizations with vocalization sound effects generations with physical modeling and how sort of like existing physical models can be improved or adapted using uh, modern machine learning methods to sort of like learn the control parameters, potentially improve the models themselves. And yeah, I've been involved with Nemesindo for a bit over a year now as well. And in that, I've mostly worked on sort of like adapting like a large back catalog of existing models to newer platforms, and that's sort of like the tooling thing is one of the challenges as well. And I'll just quickly share my screen here. Uh, yes, there we go. Going to take over the presentation here. Um, One thing is, yeah, we're we're targeting sound designers, so we want to make tools for sound designers that work for games, and there is a quite sort of large and diverse landscape of tools out there. Um, so there's different game engines, Unity, Unreal, Godot, which each of them have sort of like their own audio system that people use, and they have their own sort of plugin system. Unreal recently introduced Metasons as well, which is sort of like a graphical Max MSP-like framework for audio. Then there's middlewares that other people use instead of the native game engine audio, like Wise is a very popular one, and Fmod is another one. Uh, and then there are sound designers that are not even necessarily working with the game audio software, but rather would like work a lot in digital audio workstations and then sort of like send their work over to more technical game audio programmers. So there's a lot of tooling involved, and ideally we want to be able to have a model. Once we have a really good sounding model, we want it to be available to people working on all of these platforms. So for that, we've been we've been working on an internal tool that does that. Where we make heavy use of templating. So we sort of separate out the interface of a model that is the same on every platform, which would be like what are the number of output channels? Is it a stereo model? What are the control parameters and sort of any presets? And from those descriptions, this might sound pretty familiar if you've worked with something like Juice as well. This is sort of like a specific solution targeted specifically at uh, procedural audio sound effects that only generate audio that don't need to do any sort of like um, effects. They don't need to really process input audio and these sort of things. So it's really specifically targeted at this is an adaptive, interactive procedural sound effects. So once we've defined the whole thing, we can generate a bunch of sort of like skeleton core code, implement the actual model DSP in C++. We'll also generate a bunch of tests if you've prototyped the whole thing in something that's easier to iterate on, like Pure Data or Python or these sort of things. There's also automated tests to make sure that the whole translation actually like does implement the same DSP. And finally, this is where we then work with templates and sort of like project templates really heavily. We can generate sort of like target projects for a bunch of different platforms that take the previously compiled model and bundle it as a project that is ready to be deployed. Sort of like one of the models that we have had for a while. This is largely based on one of the Andy Farnell models that was mentioned earlier. This is sort of like an example of what that could look like. We have a few control parameters for an explosion model. So there's the rumble, which is sort of if you have an explosion, the sort of like initial shock wave that also goes through the ground a lot. Then there's the, sort of like more hissy sound that propagates through the air, and then sort of like the dust that is thrown up by the whole thing. So this is very much perceptually motivated. So this is not really a physical simulation, which in case of an explosion would be completely prohibitive because it's sort of like very complex physics. But this is sort of like a model that looks at what does an explosion sounds like, what does an explosion sound like, and then sort of builds a DSP model to emulate specific elements of that. And yeah, this is an older model that we've had in the back catalog as a sort of web audio implemented model for a while. And I'll quickly show what that looks like. So yeah, this is the Nemusinde website where there's a bunch of different models available that are all implemented in web audio. And yeah, there's the few control parameters. There's a bunch of presets, and then yeah, depending on the actual settings, the same model would sound quite different. Yeah, for sort of like more distant blasts. So yeah, sort of just adapting to the control parameters depending on the characteristics that are desired in this specific one. So what that would then look like if we want to take this model and which we've had for a while in a sort of like web audio JavaScript implementation. But if we now say we want to make it available on a bunch of different platforms, then with our current tool, let's see. Oh no. Okay. Second. Right. With our current tool that we've developed for this kind of yeah, to deploy this on as many platforms as possible, there are a couple of sort of YAML files where the interface is described, control parameters, whether they are sort of floating point numbers, whether they're integers, booleans, triggers, different types of audio parameters that basically everybody who has done some audio programming on in basically any sort of framework would recognize. Then there's a format to describe a couple of different presets. And then we've set up a system that does a bunch of automated boilerplate code generation, a few sort of like sanity checks, making sure that the reported duration is accurate, that there's no clipping going on, that nothing gets numerically unstable. There's a few automated bindings generated to WebAssembly so that we can sort of like bit by bit replace some of the large web audio catalog that we have on the website with this new implementation, while still sort of like serving it on the web. Python bindings are generated automatically for sort of like prototyping and testing as well. And yeah, then the whole thing as a sort of like as an interface that just does all the bog standard audio generating DSP tasks. This interfaces to actually like fill a buffer, generate audio. This interfaces to affect the control parameters. Under the hood, there's some automated interpolation of control parameters going on depending on how big the buffer is, like depending on the control rate that we get from different host platforms. Um, but the uh, but the main thing is that you this is sort of like an excerpt from the actual DSP that you would then implement in C++, and that then generates a bunch of different backend projects. So I've for the demos, I'll show the WebAssembly and Wise. We are what we're also currently working on is both Unreal Native Audio, Unreal Metasounds, Unity, and eventually VST. Um, Sort of just the same, or coming from the same C++ DSP code to make sure that it's actually the same audio every time, and that whenever we make updates to the model, we won't have to go through a bunch of different projects and update it everywhere. Um, so the sort of like new implementation of the same model, this is currently served locally. This is just now this is not running from the website in Web Audio anymore. This is from the C++ code that was compiled to WebAssembly and then sort of loaded within a Web Audio worklet. This is just sort of to show that uh, all the presets or the control parameters, the different audio generation, like all this boilerplate is generated automatically. You just have to write your C++ DSP code, and then you get the same thing as we previously had on the website. And then the same thing again as well uh, for, no, I need to quickly switch the screen share. And now the same thing as well from the same DSP code, also to platforms that are relevant to game developers. In this case, for example, Wise, where see again the same sort of presets, the same control parameters, where these would be used within Wise, which then offers sort of takes care of all the interfacing with the game. So this would now be very easy for a game to send these parameters um, to control any of these parameters sort of from whatever is happening in the game. And again, it's the same. It's the exact same DSP. It's the exact same audio here. With all the different settings. So this is sort of like the idea of this whole write once, deploy everywhere thing, that that we can save a lot of development time, which I think we previously spent on porting models to different platforms and these sort of things. That is one of the bigger focus, sort of like one of the focus areas that we have currently, and the other one then is it's all well and good uh, that we can show that we can deploy these models on a bunch of different platforms, but people do need to actually want to use them. And in the case of some of the models, some of the backlog models, maybe some of the older procedural models, sometimes the quality is not quite there yet. And this is then sort of like the other part of the focus. And this is something where specifically at Queen Mary, there's quite some research going on right now. So in some recent work done by another researcher who works with Josh, Yisu Zong, he developed a sort of a hybrid neural procedural model that combines the interpretable and intuitive controls that you get from a procedural model that games can sort of directly interface with, that sound designers can directly interface with, and immediately sort of like know what to expect from them, with the audio quality of a modern neural audio synthesis model, where control is a little bit more of an issue, which doesn't give you sort of like neatly labeled, human understandable sliders. And sort of like the concept, how it works under the hood, is that we take we take real recordings of the thing that the procedural model is supposed to generate. In this case, we're still working with the explosion. And then there's a neural network that predicts the control parameters for the procedural model so that the original recording is sort of like replicated as close as possible. And then the sort of pure DSP model from those control parameters generates the synthetic audio. And then there's another neural network that is then trained to, from that synthetic audio, from the procedural model, restore the real sound, to sort of sound as realistic as possible. Because the DSP is sort of like three streams of filtered noise and a filter bank that will have some limitations. And it would be pretty hard to sort of like figure out the exact DSP that makes it go as close to the real explosion as possible. So that hard work can basically be done by the neural network while still retaining the control parameters. So the whole thing is basically you in at the end, when it's done, you have the control parameters that you want. You can change the sliders. The procedural DSP model generates synthetic audio that responds immediately to the control parameters, but might not sound as good. But then there's sort of like a post-processing step of a neural network that then takes the generated audio and transforms it into a real explosion, or like a sound that is way more realistic and sort of higher audio quality. So we also have a demo prepared for that to show how that works in sound. So what I'll first play is a real recording of an actual explosion sound. And then what you'll hear now is the output of the pure DSP model. Sort of, there has been this parameter prediction network that has taken this real recording, and it has output some control parameters for the DSP model for exactly the same that you heard earlier in like on the website and in Wise, and then the recreation of this real sound by the sort of pure procedural DSP model sounds like this. And then the sort of improvement network that takes this output and makes it more realistic sounds like this. So we've gone from the real sound to the sort of final output of this whole hybrid model that sounds like this, where the match to the real sound compared to the pure output of the physical model is already quite an improvement. And then the whole thing, and that's the idea of the entire exercise, is that you do retain those control parameters. So this is a demonstration of this whole system in real time, where the parameters are adjusted, and then the procedural model generates some output, and then the neural network improves that output to sound more realistic while retaining the ability to keep those control parameters. uh, the basic idea. So that is, in my opinion, quite a drastic improvement in terms of audio quality. And yeah, we're currently working as well on translating that into some of the uh, real-time plugins that can then be deployed on the various platforms as well. Yeah, this where the idea is really tooling for sound designers, where you get the procedural audio that can adapt to anything that's happening in game while still delivering on the sound quality that you would expect uh, from samples and real recordings, basically. So, whoops. All right. Yeah, I think that's us for our presentation. We have a website where you can contact us, an email, or just look up some of the demos that we currently have on YouTube. Yeah, so thank you very much, and looking forward to some discussion on this topic.
Thank you very much, David and Joshua. Really compelling presentation. Really, a lot of great feedback regarding the style transfer aspect of this. Really interesting way to add a new wrinkle there that I have never seen before. So there are a couple questions here, a couple questions, a couple remarks. One is from Brian Michael Fuller. Hi, Brian. Can you briefly explain how machine learning works when it comes to reproducing audio?
Yes. So there are, maybe I'll just bring up this diagram here again. Let me reshare. Um, so this is essentially so in this specific system there are really two different networks. One of them takes in audio as an input, sort of like as a spectrogram basically, and outputs not audio, but really just the control parameters. So sort of it learns to control the existing procedural DSP model to be as close to a real recording as possible. And then the style transfer network that is sort of on principle it's the same principle as changing like the style of an image or these sort of things. So it is essentially it in a way it's an image to image model. It takes one spectrogram and puts out another spectrogram. And then the spectrogram has sort of like an additional step to generate the audio from that, which is that somewhat confusingly, the audio programmers usually think of something else, but somewhat confusingly, that is also called a vocoder. So, sort of like in the neural network audio world, a vocoder is anything that generates a waveform from a spectrogram. And that is essentially what's happening here, that a neural network first learns to, okay, this is the synthetic input spectrogram, and it learns basically to make the spectrogram more like the one of a real recording. And then there's another neural network that knows how to generate a waveform from a spectrogram. There's of course things like DSP methods to do that as well, but generally the neural network methods tend to have better quality there. I think you're muted.
Hit the wrong button there. Okay. So a couple questions from Sandro, uh, who asks, are these parameters given at the AI stage?
Um, so we generate a synthetic data set. We have a procedural model, and we can just uh, generate a bunch of random sets of control parameters, generate the corresponding audio from this DSP model, and then we have a data set. We have audio. We know the parameters that generated the audio, and then we can train a neural network that predicts the control parameters used to generate any sort of input audio. And that's how the parameter prediction network works. The control parameters are also given to the style transfer network. Like that is sort of conditioned on the control parameters while it's learning the style transfer.
Okay.
So I'll jump in here and add another take on that, which is what we're delivering, what David discussed, is still a tool for the sound designers to use. So they use this in the production, in the game content, or elsewhere to have dynamically generated sounds within the game, but under their control or based on the gameplay. So in that sense, it's quite different from some of the AI-based systems that are intended to automate part of the production process. Rather, we're allowing the sounds, still controlled by the sound designer, to be generative.
Right. Sandro asks, so is this different from AI upscaling graphics, whereas the AI is creating the audio using the DSP as a guide?
It's basically the same idea for sure. There is this is essentially upsampling. I mean, the sort of task of the style transfer network is really improve the quality on this. So sort of like conceptually, those are very similar.
So you're essentially using the model as and comparing that with the generative sound to improve it.
Yeah. So we take like a real recording of an actual explosion, and then uh, sort of like the one part of the network does its best to recreate that sound with uh, with the pure DSP model, which obviously won't be possible exactly. But then another network learns, okay, if I get this synthetic input, then these are sort of like the refinements that I need to do to make this sound better and more real.
Got it. Um, I had a question, which is that in terms of when speaking to companies that potentially want this, do you find any trends in terms of the challenges that you encounter? Would you say that the challenges are in the way that a game a game company might be looking to implement sound in the general sense, or what would you say are the biggest challenges there?
Um, so I'll jump in on this. First, there's perception of sound quality, and that's not the same as there being a genuine sound quality issue. Sometimes people assume that if a sound is synthetic, it must be limited and low quality. In fact, Andy Farnell told me that he was pitching sound synthesis to the games companies, and they didn't like it and they were more receptive once he started talking about procedural audio. But still, it's a challenge. There's this perception there. And then there is the diversity of sounds. So there isn't necessarily good models for every single sound, or there will always be some that need to be designed. That's why much of our approach is delivering bespoke models. A new game comes along where they have a specification where they need these sorts of sounds. We look and see what we already have, what we can deliver for them easily, what we can deliver with a small amount of extra work. Um, so then there is essentially the challenge that this is just a new technology. That's always a challenge. So it's beneficial for reasons mentioned, but also because games companies are looking for ways to distinguish themselves in the market and imagine virtual worlds where every sound can be created. At the moment, we're very limited. You create a virtual world, you can't make the sounds of everything. There's too many samples needed. But you could have a situation where if we have algorithms generating the graphics, those algorithms specify the materials, the density of the materials, and all these properties that can be used to sonify the sounds as well. So in theory, we could create virtual auditory worlds. But it's such a big step. and you really need buy-in from the game studio or game developers.
Hmm. Oh, we have a question from Ashay. Hi, Ashay. Says, hi, David and Dr. Rice. Just curious of the real-time performance slash implementation of the neural DSP method. What are your thoughts and approaches in that regard?
Hey, Ashay. It is definitely a challenge to manage CPU resources there. So these models can run in real time. Sort of like real time performance is not necessarily the issue. It's more sort of balancing the computational budget in something like a game where that's typically something that you need to share with a lot of other things. So efficiency in that regard is definitely like an active research area. There's a few things that can be done there, like pre-computing certain things, pruning down the network. Uh, and at the end, it's always going to be a little bit of a trade-off, or like the more CPU budget, the computational budget you're willing to invest, the more quality you're going to get out. But sort of like making that trade-off explicit is also something that like we're trying to work on.
So I'll add on that. There is a middle ground or compromise that I initially thought would be the way to go. So you can take one of these DSP models that is lightweight or very highly computationally efficient, and make it differentiable, put it into a DDSP, differentiable digital signal processing framework, and use gradient descent to optimize the parameters. The challenge there is that you're still limited by that DSP model. But in theory, you can make it, you can optimize all the parameters to get it as close as possible, given the limitations of the model. And perhaps you can even extend it to find the right variation on the model to, again, improve the sound quality. So we did that with the explosion, and it did improve things, but not as much as the neural DSP one. So when computational efficiency is a big issue, there's still that approach.
Great. Stefan asks, have you ever tried to use any domain-specific languages like Faust or C major for this?
Yes, initially, like some model prototyping, like played around with Faust a bit. Um, it is quite useful in that it also like generates to an endless list of different backends. Um, in in the end, sort of like the specific things that we want out of this like write once deploy everywhere core framework, I think are maybe just a little bit too specific for Faust, as in that we would want this preset description that we would want to have something that's specific for audio generating game plugins, which then also need to report a few other things back to the game engine. Um, Probably Faust could, in theory, do that, but I think it would need to be adapted a little bit. And then in the end, we're currently going with this sort of like uh, homebrewed solution. Something that Faust is still very useful for is yeah, a prototyping and then exporting to just sort of like a self-contained piece of C++, which can then be slotted very easily into this framework.
Right. Sandro asks, will this require cooperation of game engine developers to implement?
Not of engine developers, no. It's sort of so our focus right now, sort of like the products that we put out are plugins that are working within the existing plugin framework. So the uh, game audio engines all have their own sort of like plugin marketplace where we can just put up the plugins that they can be installed. For Wise, it's sort of Wise also has their own plugin format. Not really much of a marketplace. It's a bit less common. But we are just adapting to existing plugin APIs as much as possible. But the other sort of like the other side of that is also bespoke solutions working sort of like with game developers specifically if they have specific requests where the development can be a bit more targeted. But generally, we're working with existing plugin APIs.
Great. I believe that's all the questions that we have. Thank you very much, Joshua and David.
Thank
Thanks for
you.
having
Thanks
us.
for hosting us, Josh. And yeah, anyone wants to get in touch, definitely feel free to contact me or David afterwards. Well, you can just Google my name and you'll find all sorts of contact info as well.
Yeah, fantastic. And you can check them out on nemesindo.com. I'll be sure to put the website in the video description as well. Thank you for everybody for tuning in. Just a couple announcements before we sign off. Once again, if you're interested in audio software development, want to learn about audio software development, be sure to check us out in our community. You can join via theaudioprogrammer.com/community. Thank you once again to our sponsors, Focusrite, JetBrains, Juice, and ADC, the Audio Developer Conference. And be sure to join us next month for the Audio Programmer Meetup every second Tuesday of the month. But for now, we're going to go ahead and sign off. Thank you, everybody. Have a great day or great evening and happy coding.
Thank you.
Thank you.